Happy Thursday to you, friends. Just a quick reminder of what we've got going today. PLC 13 due this week on Friday. Homework 6 plus the usual homework quiz will be next Wednesday, next week. And we have a concept quiz today, and that's up and going. So please take a look at the quiz and see if you can't get that done. Usual time involved on that. So, with that being said, I think we've finished what we need to from the relativity standpoint, and we'll move on since this is really only an introduction to special relativity. And as much as it would be great to go into depth a little bit more, no can do. But if any of you are local and are interested, I would like to offer you the opportunity to take Physics 4D here at Cabrillo. It is in person only, and it is offered in the fall, but only of every even year. So this is a once every 2-year class, and it's a lot of fun. It is dedicated solely to special relativity and quantum mechanics. That's all we do the entire time. There's no lab, there's no PLCs, it's just the class. So it's a real great opportunity to do a lot of study and diving into what is essentially some of the greatest material that people have ever invented. So if you're around and you have the opportunity and the desire, then give it a thought. Might be a bit of fun. So the stuff we do here in terms of the special relativity that we've done, we take much more time on that. We're going to start quantum mechanics today and work on it from today, basically for the next about 2 weeks or so, and that's about it. In 4D, we will be spending about maybe 9 to 10 weeks doing it, so a much bigger chunk of time, and we can get into it a lot more. All right, so there's the plug on that. We are going to start with some quantum mechanics. I want to talk about the development of the quantum mechanics and the kind of historical development. How did people think about things and what happened? So this is definitely the abridged version. And honestly, it's also the physics version in which we hit all the stuff that we think is important. But by no means is this complete in any sense. One thing that I want to start with today is black body radiation. And we've talked a little bit about this, though not as much as I normally would have liked to. The idea that radiation is emitted by things, any object with a temperature. And if you recall, the power emitted by an object that has a temperature was proportional to things like the surface area of the object and the emissivity, the kind of more or less the color shininess of the object, or should I say the non-shininess of the object, as it may be, as well as, of course, the temperature. So this is the power emitted by a hot object, but due only to radiation. And this is known as the Stefan Boltzmann concept here on this. So this was proportional to, make my proportional to sign, proportional to surface area and times temperature to the fourth, which is pretty astounding. So a small increase in the temperature, I mean, typically with us in physics, we're just going to use a double. If we double the temperature, and this is on the absolute scale, right? So if I double the temperature, all of a sudden the radiated power went up by a factor of 16, which is that's a big, like, whoa, that's a big jump. All right. Um, so I want to talk about the history of some of this. And this is black body radiation is a very interesting topic, especially from the quantum mechanics view, because there is a relationship which is known as the Rayleigh-Jeans law, which I will put in quotes, but it was come up with around the 1890s or so, and it describes the basically relationship between the energy in the gosh, what am I trying to say right now? It's describing the relationship between the energy in the radiation and the wavelength. So one thing that we do here for Rayleigh-Jeans is we plot it against the black body curve. Now, I don't know if we've kind of necessarily seen the black body curve in this class. We've worked with it in the live class, and we've done some stuff with that. Anyways, I'm going to sketch it out for you here. This is generally something like the intensity. This is intensity, and we'll do frequency. We'll do frequency out here. Though I really don't like to do frequency. I much prefer wavelength, but that's okay. We'll do frequency. So short frequencies here, higher frequencies here. And so what the black body curve that we find looks something like, this is small, this is very low frequency. All right, so it looks kind of like this. Oops, that's got to tail off here a little bit. Looks something like that, which is backwards from the usual way I would draw it, I'm realizing, because I normally would do it with wavelength. So, in fact, let's do it for wavelength. Gosh, all right, let's do it with wavelength. If it's wavelength, because it's a reverse, it's going to look like this. All right, if I do by wavelength, it's going to look like that. In other words, wavelength being 0 means very, very small, tiny. This is the X-ray type of thing, right? Small wavelength. Say this is like X-ray, gamma ray up here, UV, visible. What's after that? Infrared, radio, micro, radio, etc. Right? So suppose this is the spectrum from the sun, okay? The sun would radiate quite a bit of visible. You'd see the visible spectrum is somewhere between here and here. And the peak wavelength of the sun is around 550 nanometers, which is dead in the middle of the yellow-green, which is why we see yellow-green so well. We are evolved to do that because that is the peak wavelength of our local source of light, heat, and ultimately life. So when you look at a black body curve like this, it's got some very distinct characteristics, right? There's very little going on in the very short wavelength. There's a peak, and then there's a long kind of tail off that goes over out here. So the Rayleigh-Jeans law, this is not the Rayleigh-Jeans law, though I labeled it that way. The Rayleigh-Jeans law, I'm about to point to it here, was come up with in, like I said, about the 1890s, 1895. It went like this. It followed this thing all the way up, but then just kept going. This is the Rayleigh-Jeans law right here. This thing here is the measured black body radiation curve. And if you don't mind, I'll just do black body as BB here. Measured BB curve is the red one. So, in other words, we have a great problem. The measured intensity curve in the red here is not predicted fully by the theoretical curve. In other words, the theory is not matching the experiment, and that's a big problem for theoretical physicists. So the experimentalists don't care. They know already that the theorists don't know anything. By the way, I'm a theorist. So they go, hey, whatever your prediction is, whatever your theory says, way to go, this is what we measured. And you go, oh, dang, that doesn't look anything like what we measured. So my prediction is terrible. And you can see that they predicted this thing goes way up, and it doesn't stop. It goes up, asymptoting up at the axis here. So what is that telling us? It's telling us that the amount of energy contained in the radiation of very small wavelengths is basically infinity, which is absurd, right? So the sun does not give off infinite energy at very small wavelengths. So they knew something was wrong with the theory. They just didn't know what it was. And in 1900, a fellow by the name of Max Planck came up with a way to try and figure out what this curve looks like from a theoretical standpoint. But he had to make a brand new set of assumptions, which he didn't even realize what they were until maybe 2-3 years later, as he was working through this. He came up with the equation for this from a predictive standpoint, but he had no idea what the physics behind it was. And he worked on that for several years. The assumption that he had to make was that the radiation that was emitted by anything with a temperature, in this case the black body, right, came in small discrete chunks. All right. In other words, radiation is not a continuous wave. It's not a smooth, always continuous thing. It's made up of really small chunks of things that have a wave character to them and travel together in a kind of collective way. This is somewhat like thinking of water waves and thinking of the ocean surface, right? And you see the waves breaking on the shore, and you go, oh, isn't that cute? Oh, look at all the waves. But when the wave breaks, you can kind of see it smashes, and then there's droplets and mist and things like that. And ultimately, if you look at the water, it's not a smooth sheet of water. It's not water everywhere. There's water molecules that make it up, right? And I mean, if you wanted to go a little bit less dramatic than that, there's little droplets. You can consider droplets making up the water, or molecules, if you like, right? So it's chunks of things, chunks of radiation, chunks of energy emitted by the hot object. And in doing that, he was able to make this curve mathematically. He was able to change the Rayleigh-Jeans law and make it, I don't know why we don't call it the Planck law anymore, but it's just known as the blackbody curve. But he found out what this was, but his assumption was that radiation comes in discrete packets. And that discrete packet is known as the photon. You will hear or read, or anything that you do, if you read up on the subject, you'll always hear people talking about small chunks or discrete bundles or little bits of. And it all means the same thing. We're just trying to form a way of communicating that this apparent thing, which looked to be a continuous field, is not continuous. It is actually chunks of stuff. So we'll say it comes in small chunks. All right. And each of these chunks, he says, has an energy which is equal to some constant multiplied by the frequency. That constant is now known as Planck's constant. And F is the frequency. And am I off the board? I am. Where did I leave that one? Barely left it on frequency, so we're up in here somewhere. All right, so frequency. And the frequency would be measured typically in hertz, which is the unit of something per second, cycles per second, say. And Planck's constant is turns out to be a very small number if you do it in joules, which is kind of a silly way to express Planck's constant, because this is ultimately the energy of a very, very small piece of the electromagnetic field. And that's a 10 to the minus 34 here. In electron volts, which is a much more palatable unit for this, it still is something like 10 to the minus 15 or 16 or 17. Anyways, whatever it is. It's 15. Anyways, whatever it is. It's an incredibly small number. And basically what it does is it defines the smallest possible amount of energy that can create a photon, can create light at that frequency. Okay. Now, he published the idea, and everybody, of course, thought it was a load of malarkey, because that's what we do. We don't believe anybody, and we think that everyone else doesn't know a damn thing. So, and in fact, the Royal Society, the English, or I guess really British, but anyways, there's a society of physical scientists in England, and they're called the Royal Society, and their phrase, their catchline is "Don't believe anything anyone tells you." Is nullius in verba, which is in the Latin, which means if you hear something, don't believe it. So Planck published his law, and everybody thought it was a load of crap. Well, they thought, oh, good job mathematically making the line, but this assumption is total garbage. And in 1905, Einstein published not only special relativity, which we have already talked about, but also published his analysis of what's called the photoelectric effect. So the photoelectric effect was an experiment done in the mid 1890s by a fellow by the name of Robert Millikan. He was the future president of the California Institute of Technology, Caltech, down in Pasadena. Also won the Nobel Prize for determining the fundamental charge of an electron in about 1924 or something like that. But anyway, Millikan did this experiment involving the photoelectric effect, and again, nobody could figure out why the results were what they were. Einstein came along, proposed this as the explanation to what the photoelectric effect was telling people, and then everyone said, oh, actually they didn't. They said, there, you're still a load of crap, but eventually they said, oh, I told you this was a physicist's history. So hopefully you can see that this curve here, this upwards pointing, basically this is almost like a parabola that's centered over here and is pointing upwards with an asymptote here at the axis, is telling us that the amount of intensity emitted by a hot object is heavy in the small regions here, in the small wavelength regions, which is absurd, right? It matches very nicely down here, which is why they were able to come up with something like this. But ultimately, as you get to smaller and smaller wavelengths and hotter objects, it fails. And this was rather this had a rather dramatic name, the ultraviolet catastrophe. Because as you get into the ultraviolets, right, you're talking about the energy, the expected amount of intensity at those wavelengths going sky high. Catastrophe, of course, maybe slightly overblown, but nonetheless. Let's talk about the photoelectric effect, because this is now considered the experiment and explanation which really nails down why photons have to be a model for us. So remember, as we go into this stuff, I will remind you of the thing I probably said on day one, which is physicists don't describe nature. We make models which are simple, which we think might be kind of like something we're seeing and might help describe this phenomenon here, and then we analyze that model. Nature is way too complicated, so we have to make a model that kind of encompasses all of the stuff that we think is important and that in our thinking will reproduce the important bits like the data measurements and things like that. And if we can come up with an explanation for that, then that's a good model. And if it doesn't work, then it doesn't work. And this was not a good model. Okay, but this model matches the data much better, and it includes this assumption, which we should explore, and ultimately will turn out to be a good model for what light is doing. All right, the photoelectric effect. What do you suppose the photoelectric effect is? Photo, meaning light, electric, flow of electricity. So it really is nothing more than shining light on stuff and finding that you can get an electric current out from things. All right, so the setup basically looks like a lamp here, which is going to shine light onto a, let's say, a piece of metal right here. So light is coming in this way, and I'll just use, I'll use rays. This is rays of light coming. No, I should use waves because these should be electrons coming out. Okay, we'll do this. We'll do this coming in. This is light coming in. It is impinging on the surface and knocking out electrons. All right, so just a few for demonstration purposes here. But you can imagine there is a lot of light coming out of the bulb, and when it hits the metal, electrons are getting ejected. And we're attracting them to something over here, say. All right, so suppose I have, for example, a positively charged plate right here, like this, which I'm gonna say I put a plus charge on this, so it's attracting these things, right? They're not just getting emitted and going like, oh god, whatever, right? If they get emitted from the metal, you'd know that would leave an overall positive charge left on the metal itself, which would then attract the electron back into it. So suppose that we're able to grab it from out of there and pull it. Okay, now a couple of things happen with the photoelectric effect. This doesn't require the use of photons whatsoever until you include a couple of these little factoids that Millikan found while doing the experiment. The most interesting one was that if he adjusted the light's color, right? So if he, in other words, changed the wavelength of the light he was using, and maybe he started with a blue, and then went down to a green, and then went down to a red, okay? He found out that at a certain point, there was no more current emitted, no matter how intense the light was. So we call this a cutoff or a threshold. So we can say that there exists a cutoff frequency or a cutoff wavelength, let's say, because we've been talking about wavelength. So let's talk about wavelength. There exists a cutoff wavelength above which, right? Because if I say going from blue to green to red, I'm going up in wavelength, right? So above a particular wavelength, nothing is emitted. Okay, so that's like saying, oh, I've got a cutoff, say, right here, and any light with a wavelength under this will eject electrons and make a current, but any light with a wavelength above that will not, which is kind of weird. There exists a cutoff wavelength above which no current is emitted. Or you might say no electrons are ejected. I'll combine those two and just say no electrons are emitted. How about that? This is not explainable by the wave model, right? We have so far talked about waves of light. Well, even before that, we talked about rays of light, which we found had to be abandoned. Well, not completely, but it had to be realized that that's good for some things, but not everything, right? So as soon as I try to shine light through a small hole, I can't use the ray model. But if I want to just bounce light off a mirror, or if I want to hit a lens and figure out where the focal point is, the ray model works great, right? But if we're talking about small holes or narrow scratches and diffraction grating, all of a sudden I can't use the ray model. I need to talk about the interference of the waves, right? Remember all this way back when? Way back when? We arrived at the idea that the ray model is not complete. The wave model has to take some of these, right? This is why we have models, so that we can figure out all these things. Now we're at the point where, now hold on, if I have waves, shouldn't waves of any energy be able to eject electrons? That's like asking the question, if I have a boat sitting in the harbor, shouldn't waves of the water of any wavelength make the boat go up and down? Yeah, it would, right? This is kind of like saying there's a point at which you can put waves past the boat and the boat won't move. Seemingly ridiculous, right? That can't be right. This is why people thought this couldn't be right. So the idea that that you can shine light above, like that has too long of a wavelength, and then not get electricity out. Whereas when you went down to a more blue light, yeah, it'll eject no problem. And even if suppose this one ejects ejects electrons when the light is blue, green, but not red. Suppose if I shine red light on there, it doesn't eject, which is too bad because I drew that in red. But anyways, no, that's all right. Even if he cranked the intensity really way up, in other words, there was a lot of energy in the waves, right? Because intensity is related to energy, right? When you go outside, or when you go, here's a great example. So I'm underneath fluorescent lights right now, and they're not that intense. But when you go onto a stage and you get one of those spotlights shined on you, and you are sweating, right? Because that's like, man, I'm burning up underneath this lamp. And that's what intensity means. So it would stand to reason that the greater intensity means more energy. But if there is a red light here and it's really blazing, it won't eject electrons. This makes no sense from the wave perspective, right? I have to get the light to go down to a green in order to start ejecting electrons. And even then, if I barely put even the slightest faint green, I take the intensity way down so it's barely even there, and it will eject electrons because it's below the cutoff. So this is getting the wave picture to look like, hey, wait a sec, this is not complete here. All right. So our second little factoid here is that the intensity of the light really, the only thing the intensity does, if you are in the region where electrons are getting emitted, it will emit more. If you are outside of the region where electrons are emitted, it won't do anything, which is really strange from a wave perspective, right? So intensity, it either changes the amount of current that's leaving the metal, or if there isn't any, then it doesn't do anything. Let's see here. If it does nothing, that means you are above the cutoff. You are on the wrong side of the cutoff. All right. Okay. So, and the third thing, which I think is a pretty cool one, is that even if you had very faint light, if you have very, very, very weak, not intense, and you're just barely spilling any out, if as long as you're below the cutoff wavelength, electrons will come out, and they will come out with no delay. There's no time delay. From the wave perspective, what needs to happen in order to get electrons out of a metal? Well, you have to do work to go in and grab them and pull them out of the metal. The metal is not just going to give them up freely, right? It's like trying to take an egg from a chicken. They're going to peck you. So you are trying to do work to pull the electron out of the metal. That energy is, in other words, energy is required to pull the electron out. So from the wave perspective, the idea of I can put in very, very weak waves, that is to say low amplitude, right? So the amount of energy in the wave is very little. And I can put that energy into the electron. So the electron can start gathering energy, and then over time, with this really dim light, it will have gathered enough energy that it can now leave. This is never observed. Either the light's shining on, the electrons are coming out, or the light's shining on and the electrons are not coming out. There's no in between. There's no like shine the light on and then wait a while and then electrons come out. There is none of that. They're either light in, electrons are coming out like that, or if you're on the wrong side of the cutoff, light on, nothing happening. There is no waiting for an electron to eject. It is already going if the photoelectric. So the other part to this is there's no time delay. There's no reason for the electron to feel like it has to build up the energy. It receives the energy and leaves, right? So there's no time delay. Between the light shining and the electrons leaving. Okay, so all three of these things are problems for the wave model. However, Einstein showed that they were perfectly in line with the predictions given by a photon model. In other words, if you look at the energy of a photon, which Planck said was equal to h times f, and if we change that into wavelength, we can say it's equal to h times c divided by lambda, right? Where we just change the f into c divided by lambda. And therefore the energy is going up, 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 as the wavelength is going down, 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 right? That's why we have a wavelength cutoff above which the electrons will not be ejected. That means there's a threshold, right? There's a certain amount of energy we need to supply to the electrons just to get it out. That means there's a particular wavelength at which that will happen. Or if you like, there's a frequency at which that will happen, but we're talking wavelength. And if I put in not enough of that, the electron's not coming out. You can't get the electron out. Okay, so that's why there's a cutoff in the wavelength here. I'll give you a kind of I don't know if mechanical is the right word. I guess it is. I'll give you a mechanical example of how to think about the photoelectric effect. All right. So suppose here that we have a deep well, and there is water at the bottom of this well, way down here. And I know that there's water down there, and I need to go get a bucket all the way down to that water, fill it up, and then pull the bucket up to the surface. All right, so the way I'm going to do that is by constructing one of those little well houses here, which has a rail and a handle here, and then around this thing is wrapped a bunch of rope, and at the bottom of the rope is where the bucket is. Okay, like so. Now, what I'm going to do is I'm going to get the bucket filled. And question, how much work do I have to do to get the water up to the top of the well here? Well, I have to do this much gravitational potential energy increase of the water, and therefore that much work. All right, so you might say there's a GPE increase here. I have to do work equivalent to the amount of gravitational potential energy that the water in the bucket has to attain in order to go from all the way down there all the way to up here. Okay? That is exactly akin to shining light in on a surface and just barely getting an electron to come out, right? That is, in other words, I'm putting energy in by cranking the handle. That's like the light energy going into the metal. And then I'm grabbing some water from the bottom of this well and I'm pulling it all the way out to the surface and just getting it to the surface. And that's the amount of energy the light would need in order to get an electron to come out of the metal and just sit there. Okay? So the GPE increase, this kind of work that I need to do, this is the work input. That is the analog to the light energy. Right? The work input, the amount of work that I'm putting in is equivalent to the light energy. And this gravitational potential energy increase, which is raising the energy of the bucket from way down there to way up there, is known as the work function of the metal. Right? In other words, this work function of the metal is how much energy is needed to raise an electron from a low energy state of being bound within the metal to coming out. Okay? The work function equals the energy, let's see, are you seeing this? Yes, you are. Okay. Energy needed I'm going to use the word liberate. I'm not used to writing so close to the chalk tray down here, but you can see that, I think. Can you? Energy needed to liberate electrons. That's what the work function is. Right? This is the minimum amount of energy necessary to raise an electron to a point where it is now it has now left the metal. in exact analogy to the amount of energy necessary to get the bucket all the way up to the top here. So it has definitely left the well, right? It's out of the depths. But one day I get really excited and I have eaten a great breakfast and I'm thinking, man, I'm full of energy today. And I start cranking on the handle, right? But I put way too much energy in so that by the time the bucket gets up to here, I'm going like, oh, whoops. What does that energy end up as by the time the bucket gets here? Well, it's going to be extra kinetic, right? So if I put in way more than just the gravitational potential energy necessary, I end up with not only the bucket coming up to the surface, but the bucket leaving with speed, right? So anything extra above the work function ends up as here's the bucket, right? And it's traveling, it probably busts right through the thing here. So it's right, off it goes. This is leftover kinetic energy. Anything extra that I put in above what is necessary to just get the bucket to here is going to show up as kinetic energy in the bucket, and the bucket's going to go flying away. And then it's going to drop the water out, and I'm going to be sad. And my tears will fill the bucket again. So the same thing is true in the photoelectric effect case. If I put in more energy than is necessary to just get the electron out, that energy goes into kinetic energy, which kicks the electron away from the metal. Okay? So Einstein said the photoelectric effect is really just energy conservation. If you think of it in this sense, the work that I did went into raising the bucket and then possibly whatever leftover kinetic energy the bucket had at the end. Yes, I realize there's a change in height and everything, but never mind that. There's extra kinetic energy by the time the bucket gets to the top of the well. Now, if you translate that to the photoelectric effect, then the energy equation, the energy conservation, would look like this. It would say, here is my input light energy like this much, right? We'll say this is the input light energy. Okay, and that is known as H times F, or H times C over lambda. What's going to then happen is that's going to move into the potential energy, or the work function that is necessary to remove the electron from the metal. Right? And if there's any left over, then that goes into kinetic energy of the electron. Right? That's electron kinetic energy. Now, we can adjust these bars because I could say, now can you see why there's a threshold? Right? There's a cutoff, and I think you can see why. If I don't supply at least, right, forget this red box at the top, if I don't supply at least this much energy, I'm not getting an electron out, because the amount I need, the amount of energy I need to get an electron out is this much. So if I go over to my input energy, and my input energy is like down here, well, I'm not getting anything. And that corresponds to not having a low enough wavelength that the energy is large enough in order to liberate the electrons. So when I look at the input energy, right here is the cutoff energy, below which I will not get electrons emitted, no matter what I'm shining on the thing. Okay, so there's a threshold. This is the cutoff. Right? Below that, I won't get anything. That's like, I went to the well and I was like, oh, I'm tired. I'm not going to get water all the way from down there up to here with a couple of cranks. it's going to get from here to there, and I'm going to be like, I'm not going to let go, and it's going to slip back down and let all the water out. I'm not going to get anything, right? So, and no matter how intense I make that, it's still not going to get the bucket all the way up. No matter if I go, if I stop, I'm not putting in enough energy to get the bucket all the way up. And the same is true with the light. If I shine really intense spotlight energy with a wavelength that is above the cutoff, I won't get anything out. Because that's just putting in lots and lots and lots of something like this, but I needed this. I need more than that in order to get that electron out. And so we just say, if we translate the bars into an equation, what we use, here I'm just going to move that HC over lambda. Right here is the HC over lambda of the incoming light, and that has to equal the work function here plus the leftover kinetic energy here. There you go. Now you're doing what Einstein did. All right? So how do we figure out the kinetic energy of the electrons? We can measure this because they're little tiny electrons with a charge, right? Well, if I change the plate's voltage to negative, right? Instead of making this a positive thing which attracts the electrons, suppose that I make this into a negative which repels them. All I have to do then is figure out at what point have I made enough voltage on the plate such that the electrons can't reach the plate. Yeah? In other words, here is a negative. If I make that negative, what I'm doing is basically like I'm making a ramp for them to go up, and I'm making the ramp higher and higher and higher with more and more voltage. Okay? When you change that to a negative, which repels them, which seems to be the opposite of what I wanted to do, but remember, we're doing science, not electricity generation yet. Ultimately, obviously, what I'm describing here is a photovoltaic cell. But right now, I just want to do the science of how fast are the electrons coming out. So we can figure that out by figuring how high of a ramp do I have to make them go up in order that they have to stop at the top. This is exactly akin to riding your bicycle, pedaling the pedals as fast as you can on a flat road, and then as soon as the hill comes, coast. Now you take your feet and you coast the pedals and you go up, and if you're not going all the way up the hill, then you didn't have enough kinetic energy to get all the way up the hill, right? But if the hill is only like this and you can make it just barely, and then you stop at the top, that's the voltage that I want, right? So the voltage is like the hill height, and the kinetic energy is what the electrons are racing in with. Right? So in order to change kinetic energy to potential energy of electrons, the way you do that is by multiplying the electron charge times its voltage. Electron charge. The electrical charge, the literal, how much electrical charge does the electron carry? Electron charge multiplied by the voltage of the plate. Right? So you can just make a circuit here by connecting these things around like this. So all I have to do is have the negative side hooked up to this plate here, positive side hooked up to the metal, and as the electrons come this way, I'm repelling them and causing them to turn around and come back this way. In other words, they're in an electric field which is causing them to slow down. This electron charge is known as little e, and then the voltage is known as delta V. Now, if I get to the right amount of voltage, I have stopped the electrons from moving through here. So this is known as the stopping voltage. All right, so E times delta V stopping is equal to the kinetic energy of the electrons. That's how we judge the kinetic energy of the electrons. the delta V, remember, is the height of the hill. It's like the electron charge is your mass, right? Or is kind of like mass, and this is G times the height of the hill or something like that, right? So you're basically doing 1/2 mv squared equals mgh, but you're doing it with electricity, so it looks a little funnier. And if you've had 4B, you kind of maybe remember this type of thing. And if not, well, maybe now you do. All right. Therefore, when it comes to the maximum, and this, by the way, is the maximum kinetic energy, right? If I want to stop all electrons, that means I've got a voltage which repels everything. And I can put that into this right here and say that now I have an expression for the kinetic energy of the electrons. Work function plus E times delta V stopping is the kinetic energy of the thing. All right. So notice a couple of things real quick. If I'm at the wavelength that is the cutoff wavelength, I don't have any kinetic energy based on my bars here. Right. So if I'm at the cutoff wavelength, all I have is that hc over lambda equals the work function. If I have a smaller than the cutoff wavelength, in other words, I'm supplying more energy that liberates the electrons and ends up in leftover kinetic energy. That leftover kinetic energy I'm now measuring with this. And I can come up with a way to figure out what the stopping voltage is because of the way the units work. All right. And this is a little bit of fancy footwork right here, but don't get too bogged down on this. The unit of the electron volt is perfect here. And the reason is because I've got an electron charge multiplying a volt. So in the units, I often will include the electron E charge. What we've got here, hc over lambda is equal to that. I'm just going to let you know that hc itself is a really useful number to know off the top of your head. hc is equal to, approximately, it's pretty good, 1240 electron volt nanometers. So if you have not ever encountered the electron volt before, it's akin to a joule. Okay, it's a measure of energy. It is 1 electron volt is the amount of kinetic energy an electron has after it passes through a 1 volt potential difference. So if you don't know what that means, imagine that I have plates like this, and there's 1 volt. I have a 1 volt battery, and I've hooked these plates up to a 1 volt battery, and I've released an electron here at the negative plate. And it's going to get attracted to the positive plate by a 1 volt battery. How much kinetic energy does it have when it reaches the positive plate? It has 1 electron volts worth of energy, right? It's a 1 volt potential difference, and 1 electron just did that. So 1 electron, 1 volt, 1 electron volt. 1 electron volt is related to the joule by the charge of the electron. So 1 EV is equal to 1.6 times 10 to the minus 19th of a joule. This is why we like electron volts, because that is a really small number of joules, and nobody likes really small numbers, and nobody likes really big numbers. There's a Goldilocks zone for numbers that we like. I don't know if that's true or not. I guess it's kind of true. I mean, like big, huge numbers, you're like, oh God, I got to count all these zeros. I mean, you know. So anyways, 1 is way better of a number whenever you can use it. So, and 1 electron volt's the same as that many joules, and so it's an energy. Electron volt is an energy. If I look at this, I'm going to notice that all of these quantities can be written in electron volts. Okay. This number here is in electron volts, and then if I put the wavelength in nanometers, I don't have to even convert the nanometers. It's already just going to cancel the units. And then I can use the work function in electron volts, and I can use this as basically a voltage. So the great thing about this is when I have a voltage that stops them, for example, what if my stopping voltage was 1.3 volts? Well, how much kinetic energy did they have then? 1.3 electron volts, right? It's a great little unit. Let's do a quick example here to try and nail this down, and then I think we're probably going to be just about done for today. So let's examine a material. Let's do this. Let's examine a material whose work function we know. All right. And let's go from there to figure out what we can find about, well, what's the smallest wavelength that I need to put in order to make the, what's the largest wavelength I need to put in order to make the photoelectric effect happen? So let's suppose that I have a material that has a work function here. Let's suppose that I have a work function that's pretty easy, all right? Let's say we have a 2 volt work function, 2 electron volt work function. All right, so we're going to have 2 electron volts, like that. That is, in other words, the depth of the well. Okay, that's the minimum amount of energy I need to put in order to get an electron out. Let's start off by finding what is the cutoff wavelength. Let's find the cutoff wavelength. All right, well, if I'm finding the cutoff wavelength, that means I'm putting in the bare minimum in order to just get the electron to pop to the surface. That means there's no leftover kinetic energy, and I should be able to write that hc over lambda cutoff is equal to W. And I need to now solve for what lambda cutoff is. Lambda c, can I just use lambda c here? It's just hc over the work function, which is 1240 EV nanometers divided by 2 EVs. Right, so my answer is going to come out in the useful units of nanometers anyways, which I'm going to be happy about. And it's going to be 620. Right, lambda c is equal to 620 nanometers. That is a very nice red. Above that, if I try to hit it with infrared, nothing's coming out. Okay, if I put in 650, no, which is also a very nice red, that's more like a fire engine red, nothing's coming out. 620 is more like a brick red. I don't know the difference, I'm just making that up, I don't know what that is. So if I put in wavelengths below this, right, if I go down to 600, well, can you see that if I do 600 hc over lambda with 600, I'm going to get leftover energy. And that means I'm going to end up with a kinetic energy of the electrons as they move away from the metal. Okay? So let's say now, if I find the cutoff wavelength, suppose that we are light of wavelength. Oops, wavelength. 400 nanometers, right, is now impinging on the surface. Shines on the surface. Now what I want to do is find out, well, first of all, has the work function changed? No, the work function is still the same. It's the depth of the well. That won't change based on what light I'm shining on there, right? What it will change is, what's the stopping voltage? right? So if I find the stopping voltage, I'm going to do it by saying, all right, E times delta V stopping, which I'll just put S down here for stopping, is going to equal HC over lambda minus W, right? And you can kind of see this working, right? Here's the amount of energy I put in. I have to less the amount that it needed to raise the surface. This is what's left over. That's what I'm looking for. Okay, so let's take a look. I've got HC over lambda. HC over lambda here is 1240 EV nanometers. I'm going to have 400 nanometers coming in. Nanometers are going to go away. I'm going to less this by 2 EVs. And I'm going to ask, okay, what's the stopping voltage? So 1240 divided by 400 should be hopefully 310, 3.1. Hopefully this is 3.1 volts. 3.1 EVs. So 3.1 less 2 is 1.1. 1.1 EVs is the kinetic energy of the electrons when they leave the metal. But I'm looking for the stopping voltage, and here's where electron volts earn their money. The stopping voltage is 1.1 volts. Because remember, this is E delta V that I found over here, equaling 1.1 EVs. And if I just cancel those E's off, and by the way, that's totally fine to do. That's not fly by night here. That's what they're for. Therefore, the stopping voltage is 1.1 volts. That's why you love electron volts, because the voltage is exactly the same as the energy. All right, that means when I make a setup like the one I erased here, I have to dial my battery up to 1.1 volts, and all of a sudden I'm going to repel all the electrons that are coming off. All righty. So you can play around with stuff like this. You can say, okay, suppose that I'm putting in light, but I find that the cutoff wavelength is such and such. What's the work function of the metal? What voltage would I need? Or you can say I'm putting light with this much energy, with this much wavelength in to hit the metal, and I'm stopping them with this voltage. Find out what the work function is. What's the cutoff, right? You can go through and change this around. And so I'll give you some practice on this stuff in the homework, which is showing up starting next Wednesday. Right? I'll get that posted soon so we can get started on it. All right. So what else do we have to do here? I think the biggest thing that comes out of this is that, well, I guess there are two things that I can think of that come out of this. Number one, the photon model is really a great model, and it works really well. This was the beginning of understanding why and how the photon model works. So the second thing is energy conservation is still our friend, right? Energy conservation, conservation of momentum, still our friend, which we're going to talk about in the next piece that goes along with this. Those conservation laws are still valid. It's not like, hey, just because we're now talking about atoms and photons and electrons, all of a sudden energy conservation is not valid. Energy conservation is valid for everything, as far as we can tell. It's just a matter of using it and finding out what happens to the energy. Gosh, I was just going to say something really great about this. What was it? So what is this doing for us? What this is doing for us is this right here, telling us that the energy of light is now contained in the, if you like, I'm almost always going to go towards the wavelength here. I mean, you can use HF if you like, but the frequency, that falls into one of those two big numbers for me, 10 to the 15th. My mind is struggling to figure out 10 to the 4. So the energy of the light is in the wavelength. It's in how closely spaced are the peaks, not, as was thought previously, the amplitude of the wave. This is very strange, because the amplitude of the wave for every other wave is related to how much energy the wave carries, right? In other words, if I start shouting at you, that's because my volume has been turned up and the amplitude of the waves that I'm putting out, longitudinal waves from my vocal cords, that amplitude has gotten bigger. Likewise with water waves, right? They're bigger. Earthquake waves, if the amplitude is bigger, there's more shaking going on because there's more energy in the wave. But with light, that's not quite the case. It's in the wavelength, or if you like, it's in the frequency. This is a radical shift, okay? And this is one reason the photon model has to be different than the wave model. And now the question comes, well, how do photons arrive? What are photons? Where did they come from? What's their origin? What happens when they get absorbed? What happens when they're getting emitted? What's happening? Well, answering that question was ultimately the beginning of describing the quantum mechanics of materials, of the atom, right? Because if only certain amounts of energy can be emitted, that means an electron can only make certain jumps. It can't make any jump. And so the kind of overarching idea of quantum mechanics is that there are certain allowed things. You can't just do anything, okay? There are certain allowed places where things can exist. There are certain allowed energies that can be emitted from things that go between those two places. And you can't just pick and choose, oh, I want to go from here to here. This is not the subway, all right? We're not going from here to there because that's what I want to do. No, we're going from always from here to here. Or actually, it kind of is like the subway, if you like. They're making actually discrete stops. I can't just stop in the middle of, hey, stop the subway, I need to get off here. Well, we're in the middle of, we're under the bay. We're in the middle of, like, you can't just stop the train and get off, okay? So maybe it is kind of like the subway then. I guess that's pretty good. Anyways, so this is the beginnings of understanding the photon model. The next thing we're going to do is an example very similar to this, which is known as the Compton effect, which is once again light shining on things and electrons doing things, and we're looking at energy and momentum of what's going on. But it comes down to, once again, a photon model being the thing that explains what we're seeing. So we're now entering the great model of the photon. This is our third model of light: rays, waves, and now photons. Of all three of those, photons definitely have, the photon model has the most power. And it's the one that we're going to use from here on out, despite the fact that I will still call them sometimes waves by accident. But the idea of the waves is that they are composed of small little things. They're individual chunks as they all move along. It's like a tidal wave of cockroaches. You can't see the individual ones as they sweep down the hill towards you when the apocalypse happens, but you know that they're there. And with that thought, I will leave you for a great weekend. Remember, your lab projects, I extended your due date to Sunday, so you have the weekend to work on it. The portal's open for your submissions. If you need equipment and are local, please contact Julia to get equipment from us that might be useful for your experiments. Don't forget quiz today, which is up and running, PLC tomorrow, and then we'll be hitting homework and another quiz on Wednesday of next week. So with that being said, have a great weekend, folks. I'll see you back here on Tuesday of next week. All righty? Enjoy some quantum mechanics world.